All right, let's take a look at 3.44, the example here. It says the position of a dragonfly that is flying parallel to the ground is given as a function of time by this function here. Of course, measured in meters and time in seconds. At what value of t is the velocity vector of the insect make an angle of 30 degrees clockwise from the positive x-axis? And at the time calculated in part A, what are the magnitude and direction of the acceleration vector of that insect? Okay, so in order to figure this out, so we want our velocity vector to look like this, 30 degrees clockwise of the positive x-axis. And we want to know what is the time that this occurs at. So in order to do that, we're going to first need a velocity equation. So we're going to go ahead and create that equation. So taking the derivative here, we get 0.18t, that's in my I hat direction, plus negative 0.045t squared, and that's in my j hat direction. And that's going to be in meters per second with time in seconds. And so what I know then is that this I hat component, my 0.18t, and my other component, my negative here, 0.045t squared, they have to be such that the time produces a 30-degree angle. For that to occur, I'm going to create an equation here that the tangent of 30 must equal the opposite over the adjacent, so 0.045t squared divided by 0.18t. Now there is one solution that kind of works here mathematically. So if I move this over to this side, t0 works. And so you might be like, oh, at time 0 it is. But we have to think about physics is just uses math to describe that motion. So this isn't actually a solution. What it means is if I plug 0 in here, I see that the velocity is 0. Does it have a direction if it's stopped? No, and so that's not the solution, the mathematical solution to the problem we want. So what we're going to do is we're going to get rid of one of those t's, and we're going to solve for that other t. And so we'll multiply the 0.18 over, divide the 0.045 over, and we'll get a time of, I covered it up. We're going to get 2.3 seconds. So at 2.3 seconds, this condition will be met. All right, so part B then wants to know, what's the acceleration vector look like at this time? And they want it in magnitude and direction. So it's more than just me taking the derivative and plugging in that time. I then have to take those two components and find the magnitude direction. So my acceleration function, go ahead and take the derivative of this function. I get 0.18 I hat plus negative 0.09t j hat. That is my acceleration function. I can plug in my 2.3 seconds here, and so I see that it's going to be 0.18 meters per second squared in that direction. And when I plug in the 2.3 there, I end up with a negative 0.208, so 0.208 meters per second squared. So now I just need to find my magnitude and direction. We'll do a little Pythagorean theorem, 0.18 squared plus 0.208 squared. Take the square root of that, and we end up with a magnitude of 0.275 meters per second squared and then we're going to do our inverse tangent function. So similar to what we did here, we know these two, we just going to find the angle. So we're going to take the inverse tangent of 0.208 divided by 0.18, and I get 49 degrees. We're not quite done because we need to give it a reference, and so we'll note that this 49 degrees is clockwise of the positive x-axis. And there is our part B. There you go.